So long story short, I changed headsets during the recording of my FEM lesson. But yeah, apparently the sound was muted, so I didn't record any sound on the tutorial, which is an hour and a half long. I'll try to compress it into less than this time, because it was a little bit too long and I had some errors there, but I ended up doing a good simulation, good wrinkle simulation. So the goal here is going to be making a nice wrinkle simulation on top of the vellum one. So I made a network box here. I'm going to color it like something like this. I object merged the original quad mesh that I had before. And I'm going to also copy and paste the object merge that contains the simulated the simulated tetras. So I'll make a null here, which is going to be the null that points to the simulated tetrahedral mesh. Geotetras animated goes into the geometry. We'll connect it to the clean version of it, so we have a minimum of parameter of attributes here. So yeah, this is the simulated version, tetrahedral version, and this is the clean quads static mesh. So yeah, we'll jump right into creating our FEM simulation. The goal here is to create a core geometry that will drive the entire body and two skin layers that are on top of it. In order to do this, we'll be using the original mesh, and we'll be transforming it into a volume first with the aid of VDB from polygons. So we're going to transform this into a volume, a quite detailed volume with a resolution of 00012. So this time we'll be doing some operations with this volume because we need to make 3 layers out of it. So first we'll do a convert VDB and convert this to geometry, and you'll see why. So basically we're reconverting into geometry. This is going to be our first layer, the top skin layer, and now we'll do some VDB reshape operations, VDB reshape SDF, and we'll, instead of dilating, which is by default, we'll erode it by 1 voxel, and do another copy without dragging the node and eroding it by 2 voxels. Yeah, so we have 1 geometry, and we'll copy the convert VDB on both of these, and we'll have the first skin layer, the second skin layer, and the third is going to be the core. Every time it's shrinking in volume, so the goal here is to make a remeshed versions of each of these layers. And the remesh, I'm going to hit escape, disable this, and set the parameters that I found that work. 10 iterations for the remeshing, the smoothing to 0. Often when you have really precise geometry and you have tips like this, very sharp like areas, the smoothing will just kill off that detail. So if you just leave it at 0, 1 or more, it's going to just round this off. So I'm going to set to 0, and the size for remeshing is going to be 0.025. So you'll see why we're doing this. Like, let's remesh this and see what's happening. Basically, I want to obtain a more detailed mesh than the original, because if you look at the original is like this, and the remeshed, it's quite pretty much the same, but we can push it as far as we can, as far as we want, because the remeshing detail that we set here is going to decide how much detail in your wrinkling you have. This layer, this skin, is going to be the one that creates wrinkles. So for wrinkles, you need some more geometry, basically. So we're going to disable this remesh node and copy it 2 times. And we're going to name these guys with nulls just so we can reference them after, or just have them organized properly. Symbiote skin level 1. Duplicate this and duplicate this again. This is going to be skin core. So we have 2 skin layers here and 1 internal core layer, which is going to control the whole body. We're going to use a lot of internal attributes that FEM solver uses, and one of them will be fuse PID. I'm going to create an attribute with attribute create this time. Usually I don't use attribute create for creating the attributes, but for FEM it's quite mandatory, because we have to have a default value of -1 for the vertices that do not have any data on them. Basically, -1 would mean that the values on this vertex are invalid. So I'm going to create an attribute called fuse PID, which is a point attribute and an integer with a default value of -1. With a default value of -1 and initial value of 0. So this is mandatory. It's crucial to have this, and the size of this value is 1, so it's not a it's just an integer, plain integer value. And then we'll make a attribute triangle, and create on top of the attribute create, assign some values to this fuse PID. I'll explain why we need this. So the fuse PID will be equal to the PT_num. Let's display this attribute, and the attribute is going to be its color by default, but we need just markers. You have a bunch of numbers here which represent the ID of these points. So we'll also group this. We'll name it interior. I mean, it's going to be a point group, interior, or maybe let's make it a primitive group. Yeah. So interior, and we'll merge these guys together, all of them. This one, this one, this one. Merge them into one. Move this one here. Move that one there, just for the order. And we have 3 objects merged into one, and you'll see why we have the fuse PID here. So let's make a clip node. The clip will help us debug stuff inside the mesh because we'll be using it a lot. As you can see, we zoom onto the edge, and we have 3 layers here. Let's make a connectivity so you can see it better. Connectivity, yeah. Connectivity class, marker color, random from attribute, and that's it. So as you can see, we have 3 colors: purple, green, and red on the outside. The purple represents the inside, the core. Green and red are 2 skin layers. The goal in FEM, in this simulation, is to create 2 skin layers that are sitting on top of an internal core layer. The core layer will be controlled the 100% by the motion of the vellum simulations we've done earlier, and the red and green layers will be simulated by FEM. So yeah, this is for preview purposes. So yeah, we have an interior group, which is a primitive group that contains all the triangles. Now we'll make a Tetconform, which is you already know this node, and the Tetconform will fill up our internal core with tetrahedrons. But don't forget that we disabled those. Press escape. We disable those remesh nodes because we need triangles in order to make proper tetrahedrons. Otherwise, we'll have a lot of issues during simulations. You see that it created 3 layers made out of the qualified mesh, which is output by the convert VDB. So I'll come back when it just lets me stop this operation. So yeah, just let me back in. We have this tetrahedral mesh. As you can see, it's quite detailed at the surface, and it's simplified in the middle. The deeper it goes into the tissue. And also I turned on the remesh, and it's going to take a while to remesh, but again, it's reevaluating the triangles and the remeshing into triangles. But I'll show you an example of what usually happens when we use FEM for wrinkles. This is a simulation I've posted on Twitter before. So this is my octopus churro that I use for a bunch of different experiments. So basically, yeah, the motion is driven by vellum, but the wrinkles are done with FEM, so it's a secondary pass. As you can see, there's quite some detail in the mesh, but the resolution of the mesh is quite high because, you know, Churi is a big guy. He's like 2.5 meters wide, and yeah, there's a lot of geometry to cover, and yeah, so I think this is the best example for the system because I used exactly the same system for Churro. So yeah, now we triangulated all these guys, so we have 3 layers, but I forgot to do something. I wanted to link this target size, copy parameter, paste relative references, and it's going to reevaluate, which is dumb in my mind. Paste relative references, and I'm going to multiply this value by, oh wow, just go back and multiply this by 1.5 and make the internal core layer a little bit less detailed. So yeah, so it triangulated this guy. I'll show you what happens when you have a fuse PID attribute created on the core with the default value of -1 and the initial value of 0. So basically, this -1 value defines the default value if there's no data assigned to this attribute. So if we go in here, we merge all these like triangulated meshes together, you'll see that Only the vertices that were assigned some data, they have anything but -1. So we go here, we display the fuse PID. So you see that our core layer has numbers, IDs, and the other two, they don't. And this fuse PID, if you change the -2, for the initial value, you put -2, the meshes and the objects that don't have anything assigned to the vertices, they will be -2. So let's leave it at -1. FEM understands that when it's -1, it's an invalid vertex for like this attribute doesn't have, there's no attributes on these vertices basically. So let's leave it like this, and yeah, we conform this skin core. It's transforming into tetrahedrons, as you've seen before. These are some really expensive operations, especially when you have big meshes and detailed meshes and big monsters. And we will add another group operator here. We'll call it inner. So this is going to be the inner part of the mesh. It's going to be a point group. We'll be adding the step conform here now. So basically, let me do the flow, the entire flow here, and then we're going to save this geometry because I don't want to spend time evaluating these things. So the tet conform, the only difference between this tet conform and this one will add surface triangles. So it will add a layer of polygons on top of the tetrahedral mesh on the outside. Okay, so now we'll be group promoting our interior points. So the interior will be promoted to the points because it was a primitive attribute, and we'll blast that interior group. Okay, and now I'll come back when I evaluate this tet conform, and I'll show you what's happening. So it re-evaluated the whole thing. Now, because we merged 3 triangular meshes into one with some fuse PID attributes, some of them are invalid, which are -1, we're going to clip this to see what's happening inside. This is crucial just to debug what's happening in your mesh. And you'll see clearly that we have some PID attributes only on that connection between the core layer and the 2 skin layers. So you see the 2 skin layers are clearly defined, and this separate kind of surface, this is the surface triangles that we added here in the tet conform. So everything looks good for now. What we're doing now is promoting the group. Yeah, so we're promoting the interior group. So now the interior group was a primitive attribute, and now it's become a point attribute, and we're blasting the interior. So let's see what it does. Now we're left with the 2 skin layers plus the surface triangles that are on the outside. So we basically remove the tetrahedrons that are outside. So the next step would be merging this inner group that we had before with our with the reminder of our operation, blast operation. So we'll also add we'll duplicate this group. We'll call it outer. And the outer group is going to be also points. And we'll merge these guys together, the outer and the inner. And now we'll move this clip node over. This is how I usually work. I just move my clip node lower and lower every time, reevaluating and see what's happening in the next operation. So we have the internal core, the skin layer, and the surface triangles. Okay, and for optimization purposes, we'll just save this guy. And I already made a file cache in my previous attempt to record this tutorial. I called it geocast geosymbiote fem type mesh v01 bgoc, and I'm going to save it. So now we have this really nice mesh, which has 892,000 tetrahedrons, 143,000 polygons on the surface, a fuse PID attribute, a bunch of groups that we'll be using during the simulation. And the next step would be creating an ID attribute. So this is not going to be a fuse PID, but just an ID attribute. We actually can go back and steal this attribute triangle. And instead of fuse PID, make it an ID. And we'll create in a safe manner again an attribute with an attribute create. Attribute create. We'll create again an internal attribute that is recognized by FEM solver, which is called solid shape stiffness. And it's a float. And yeah, as a default value, we'll use 1, and the initial value will be also 1. So any part of the mesh that doesn't have this value assigned, this attribute created on it, will have a default value of 1. And let's blast this inner part, and only the inner part. So we'll leave everything, we'll remove everything except the inner part. So we are left with the core. And I want to assign a higher solid shape stiffness to this part of the body. So if you see, we disable it, we have the skin removed basically, this blast node. So we removed all the tetrahedrons that are outside, and we'll group expand. We'll group expand the surface points. So we're going to group expand the surface points. So the surface points of our inner primitive group. So what's going to happen here is we're going to remove only the surface of the tetrahedral core, basically, and yeah. So blast. Oh yeah, I blasted the inner part, but I should have blasted the outer. So the outer, so basically we're leaving only the outer part and group expanding by the surface points and blasting the surface points. I just made a mess. So surface points. Yeah. Yeah. So basically we're going to, yeah. So basically I'm going to set the, let me clip it, see what's happening there. Yeah. So clip. We're blasting the outer, or leaving the outer shell basically, and the group expanding this guy, and we're applying, yeah. So what I'm doing here is blasting everything except the outer layer, group expanding, and then group expanding means that we're kind of expanding inside the mesh, and then we're blasting the surface points. What happens here is we're gonna apply a different stiffness to our first row of vertices that are inside the core, and you'll see why. F solid shape stiffness equals, and I'll make a channel which is gonna get the name of stiff. Click on the slider button, set it to 4, and we're going to copy this by ID to our original mesh, which is the entire mesh, and we'll set ID as a matching attribute. Whenever you do this kind of stuff, you can create an ID attribute before, do some operations like blasting and working on a separate part of the mesh, and then you can copy the attributes back to your entire mesh by ID. It will copy all the data that you applied on this part of the mesh onto the original mesh. This works also very well when you have IDs on an animated geometry. You time shift it to 1, and you do operations, and then you copy back your attributes to the moving geometry. We'll do it a little bit later also. You'll see how it works. And we're going to copy the solid shape stiffness. Let's see what we've done here. And the clip node is not supposed to be here, but it will be here, and you'll see what happened with our solid shape stiffness. Let's visualize this attribute. It's going to be a number. Like if you put it to 4, you'll see. Yeah, so I did a mistake here. Instead of, we're deleting basically the skin layer. So we're left with the core. This is what I wanted to do initially. I was a little bit confused by my own setup. So we're expanding the selection of the surface points, which is the surface of this core layer, and we're expanding it by 1. So it's gonna expand the group by 1 row of vertices, and we're removing the surface points. So we're basically trying to select the next row as vertices inside the volume of our core mesh. This is what we've done. We apply the solid shape stiffness to the inside to that layer of vertices, copy the solid shape stiffness to the original mesh. Now we're clipping the mesh just to see what happens. So as you can see, at the boundary between the core mesh and the two skin layers, we have this attribute which is higher than the solid shape stiffness on the outside. So it's 4 inside and 1 outside. This is going to act as a stiffness inside the FEM solver. It's going to override entirely the shape stiffness inside the FEM hybrid object that we'll create. And next we'll create an attribute triangle again. Let's copy this one so we don't really create it again. Not the best one. We'll remove this parameter, except remove this guy. I'm lazy just to create another attribute triangle. I've done this setup a few times prior to this. So we'll create a pin to animation attribute, which is an internal attribute recognized by FEM also, which says to FEM that this specific group, which is going to be the inner one, which is inside the core mesh, will be obeying the animation that comes from vellum. The blue one, which is the skin layer, will be simulated, which will not be, basically it will be attached to this red boundary, but it's not going to be pinned to animation. So if you want to visualize this pin to animation, if you want to visualize any attribute, you just hover above the node, click I, click onto your attribute, and then it's going to be added to this list if you didn't know about it. So yeah, where pin to animation is between 1 and 0. Now it's random by attribute, but I want to make it ramp attribute. So the red zone is going to be pinned to animation. The blue one will be obeying or following the red part, because there will be internal collisions. So next we'll make an attribute called, let's rename these guys, because set stiffness core. This one set ID. Then this will be set pin to anim. This will be set rest and set rest. And in this attribute triangle, it's a special one. We'll remove the group that we used before, disable the display of attributes, and I'll create 2 attributes called v material p. It's a vector attribute, and v base p. So yeah, these attributes, they represent the rest state of the mesh on the first frame. It's used internally by FEM to know the initial state of the mesh. And if there's no material p, it's going to switch to base p as a fallback attribute if it doesn't find material p. So, and the opposite, usually if it finds one of these, everything is going to go smoothly. These are rest attributes as if we're creating a rest position. So the rest, as you remember, it's a node that creates a rest attribute. It takes the position from the first frame of the timeline and it applies it into a separate attribute. Same goes for FEM, but these are specifically named attributes that you have to obey basically and follow. We have this master transform that we used before, and we already instanced referenced it here in order to create the clean animated mesh, the quads that are animated. So we're going to copy it here. When you copy a referenced node that has referenced channels, it's going to be referencing the original. So I'm copying the master transform, and now we'll do some more groups. I know there's a lot of groups, so bear with me here. We'll create a group called Tetrahedrons. A great thing that was added to this group operator is the geometry filter. So we'll use the geometry filter to select only the tetrahedrons. So all tetrahedrons are selected here. No polygon meshes are selected here. So if you see the group will be containing 892,000 primitives, exactly like the tetrahedrons group here. Same, we'll create another group which will be called polygons. And instead of tetrahedrons here, we'll use polygons. And the polygons group has 143,000 as the polygons field here. So, all right, and now we'll be copying this guy over, naming him set collisions whole. And we'll create 2 other attributes that are internally used by FEM, and they'll be applied to primitives this time. And we're applying this attribute to all the primitives in the system. Collision ID -1. And I will copy this guy over and name it exterior collision ID. So we're basically applying invalid values to all primitives in this attribute. So all the primitives will have this as a collision attribute, and which means that collisions are basically disabled everywhere inside the mesh. And we'll duplicate this guy again, set collisions. We're going to re-enable all the collisions only for we'll leave just the exterior collision ID, but we'll set it to 0. So basically 0 means that the tetrahedrons will be colliding between themselves and the outside colliders. So yeah, so it's also a primitive attribute. So let's see. Yeah, we don't have to visualize this because we know what happened here. So now, yeah, so the tets will be colliding with all the outside tetrahedrons and other objects. And now we're quite ready to connect this thing to the FEM solver. So let's create this FEM solver network. In the first input goes our geometry, and in the second one you'll see what goes here. We're gonna pull our animated tetras, and I'm gonna time shift this guy, delete the channels, make a point deform, and we're gonna pull the geometry that comes from the master transform here, connect the time shift to the second input, and the animated live geo to the third input. Yeah, so it works. Our tetrahedral mesh is following the vellum simulation. And what we're going to do here is work on the FEM solver first, and then we'll come back to this point deform. I will actually connect the second input. So the first input is a static tetrahedral geometry with all the shenanigans and attributes and whatever. And the second one is the animated version of it. See the animated version and the static version. Now we'll go inside the FEM solver, but first we'll name it FEM wrinkles. Enable it, go inside. Now let's create a FEM hybrid object. Why a hybrid object? It's because we have a geometry containing polygons and tetrahedrons at the same time. We'll disable particle and rod, we don't need these, but we'll use the shell and the solid, which makes sense because we have a shell, the skin, and the solid. The skin is the outer polygon layer, which is controlled by these attributes, and the solid is all the tetrahedrons in the mesh that are controlled by these parameters. I'll change just a few parameters. The shape stiffness of our shell, let's say 1000, and just for the beginning parameters. The shape stiffness doesn't really matter because this is the solid shape stiffness that we defined earlier. So this is, let's put 16, but it doesn't really matter. It's like it doesn't act as a multiplier, the value that we've set before. So, and the volume stiffness is going to be 100. This will define the stiffness of the tetrahedrons contained inside the two skin layers that we created. As for the repulsion, we're going to set this repulsion at the highest possible limit. Let's say, I mean, it can go higher, but I'll leave it at this. And the friction at 0. I don't want to have any friction on contact. So now we go into the deformation tab, and in the deformation tab we have to tell them which object is going to be deformed, which is the initial basically geometry that we are connecting. So let's type in a backtick, op, input path, 2 dots represent basically the current geometry that goes into the solver, and because we're basically by going back a level. If you can type a slash there, but it's not going to make a big difference. So we have this, let's connect it directly to the output, and we see that we are pulling the static geometry. Nothing is getting solved here, and we need a target deformation because we really want to deform this mesh by this guy. So this is the live geometry that is in the second input. So the second input has the index of 1. So it's all good. Let's add the FEM solver here. I'm going to think for a while, read the point deform, realize that there's movement there, and we'll change the solve method to, we'll leave it to GNL. The GNL is a solver that just, the GNL is a solver that is a little bit faster and needs less computation steps to solve stuff. I use GNL, I don't GSL has some limits. You can read about that in the documentation. But I'll also change the integration to the second order. This is another parameter that defines how things are solved inside FEM. But yeah, I'll let you read about these more in the documentation, which is quite amazing, if I may say so. Because yeah, Houdini's documentation is top-notch compared to other software. So yeah, the FEM solver is set. In the collisions here, we'll also check self-collide each component, connected component. So there will be internal collisions between the tetrahedrons of the skin and so on. We can disable this and it's going to be a little bit lighter, but you'll have penetrations. If there's a lot of deformation in your mesh, you'll have a lot of penetrations. We'll leave everything here. We're not going to change anything. Just let it be like this. And we'll add some gravity, even if we don't really need a lot of it, because our skin layer is already linked to the core layer. And it's not going to play a big role here, except if you have scenarios where you want to have a lot of jiggly fat that is getting pulled by the gravity and you have hanging pieces or sacks of fat or organic tissue. Yeah, the gravity is going to play a big role there. But here we have a really tight skin around an internal structure like the core layer. So let's also add a constraint, which is called the FEM fuse constraint. We'll add it before the gravity. And the FEM fuse constraint is a special one because it will allow us to connect our skin to our core using the fuse PID that we created earlier. So let's name our FEM object as a symbiote wrinkles, just so we can reference it properly. We can have a bunch of FEM objects here merged together and solved by the same FEM solver. So this is why we have to name them properly, because in the constraints like the FEM fuse constraint, you'll be able to recognize the objects in the list better. So we're going to connect the symbiote wrinkles to symbiote wrinkles, but instead of using point groups, we'll be using a identifier point attribute, and by default it's set to fuse PID, the attribute that we created earlier. So fuse PID here, fuse PID here. It's a good thing that they have two fields for the fuse PID, because maybe you change the fuse PID into something else on the other piece of geometry, and you can set two different attributes here. And the type of the constraint is going to be hard. And when you use the identifier point attribute here, you don't have any guides showing, so these parameters are not going to work. Yeah, so we're kind of set here. The only thing left to do is let's create a blast right here before the pin to animation. And what I'm going to do is select this arm in the middle. Let's do it again, like this. Click enter, delete non-selected, and we're going to work on this single arm. You can see that there's two skin layers outside and one core layer here. And let's test if our simulation even works. I'll save this as this guy, because this is the scene that I was trying to record. Let's call it 8A. Oh yeah, you didn't see the... So basically I'm saving it as this guy, 8A. Saved. Now the scene is saved. Let's activate our solver and see if the wrinkles are even working. Because of the procedural nature of our software, we can really clip just a piece of geometry and see if anything works here. And as you can see already, there's some wrinkles already in the beginning. On the second frame, we already have the wrinkles creating. So you have a bunch of wrinkles on the arms, and the detail of these wrinkles is defined by the remesh nodes up top. They will define how detailed is the skin on those arms. And yeah, it's quite cool. We have the system working straight away, which is great. We don't have to debug anything. In the previous attempt, I had to debug a few things, but now it's working fine. So you see that when it compresses, the arm creates a bunch of wrinkles, and it's going to look good, as in that octopus we've seen earlier. So if you compare the point deformed mesh with the wrinkled FEM mesh, you can see that it's solving the last frame, apparently. Yeah. So yeah, this is the big difference between the two meshes. So yeah, let's so let's do one thing. I'm going to disable this, but I'll show you what I'm going to do with this. this point deformed version, I will add a, because my goal is what? Is to create a wrinkle simulations only on the arms. I will simulate the entire body with the wrinkles, although I can set the simulation in a way where only the arms are getting covered in the wrinkles by pinning to animation everything everything except the arms. But I prefer to have some control over the areas that are affected. So yeah, we'll create an attribute triangle here. And the attribute triangle will contain a rest attribute. This time is going to be a simple rest. And this rest is going to follow the animation. As you can see, there's a little clock here. It means that the rest changes at each frame. So I will attribute copy this rest attribute by ID rest. So the rest attribute from the point deform, from the animated version that comes from Vellum, will be transferred to our FEM simulation after it's done, and we'll time shift this guy. Set it to frame. Set it to frame 1, and we have to do one more thing. We'll object merge our clean quads mesh. Clean quads. And we'll do a quick attribute paint. A really quick attribute paint. And so I'm going to paint only the arms and the tail. I want some wrinkles there also. Although there's not going to be wrinkles. I already painted some kind of wrinkles here in ZBrush, but that's okay. Control-Shift drag just to decrease the size. And just limit myself here where the arms end. Yeah, that's not bad. Yeah, that's cool. So this is going to be a mask, an attribute called mask. I'll attribute blur this guy. So my goal is to make a blend between the original Vellum simulation and the wrinkled FEM simulation using this mask. So only the arms will have this wrinkly thing. I'll attribute blur the mask just to see it. So yeah, we're maybe 32. Yeah, let's say 32. Let's leave it at that. And I'll copy this master transform also here, just so we have the same transformation as the other stuff. And we will use this time-shifted FEM wrinkles simulation to attribute transfer our mask, because we have a static mesh here and we have a static mesh here on the first frame. So this is how we do the attribute transfer. But afterwards, points. Afterwards, I'll be doing an attribute copy again. Back to the live geometry, back to the animated simulation. So attribute copy here, I'll call it mask. And we'll do some optimization, attribute cast. Attribute cast. And we'll attribute cast these guys, velocity and mask, and we downgrade it to 16-bit, save a little bit of space, as we did before, and make a clean right here. And in the clean, I'll actually remove pretty much everything except V, ID, rest, and mask. And as for the groups, any group that contains the name, the word surface, I'll remove it. And now I'll just add a output node. I'll call it, I pasted it from the previous attempt. I'll call it SimFem V01, SimSymbiot Fem V01 F5. And yeah, we'll enable this wrinkle simulation. And let's simulate a few frames. Save this project. I'll simulate like 10 frames and come back. So I solved a few frames here. Now we see that we have an ID attribute, mask, rest, and velocity. And what I was saying when I said that I will blend the original mesh with the Vellum mesh, I wanted to show you how to do it. So yeah. So I simulated a few frames. As you can see, there's already some wrinkles here being created. This is the FEM mesh that was starting to get wrinkly here. And if we compare it to the original mesh, you can see that there's no wrinkles on the arm, but here we have some wrinkles, but we have an issue arising here in the bubbles. So this is why we painted the mask. I don't want to have any wrinkles on the bubbles. This is why we're going to get the tetrahedral mesh. In order to get the final mesh as we had it here, this is the animated clean mesh, but doesn't contain any wrinkles. So how do we do this? First, I want to blend the two versions of our simulation. So let's activate this, go to the frame 3, where we have this wrinkle thing, and let's do something interesting here. Let's do a point deform. Let's copy the time shift, and let's get our static quad mesh, as we did before after the vellum sim. So we have this, oh yeah, the static quad mesh goes into the point deform, the time shift goes into our vellum, our FEM sim, and the second input, and the animated version into the third input. So we will subdivide this mesh once, because we need some detail there. And the settings for the point deform will be a little bit different. So 0, 0, 1, 5, and 5. Because when you average, the maximum points is 100, it's going to average a lot the deformation. So we don't want that. So we'll set it to 5 in order for it to respect the wrinkles. So now we have wrinkles on our quad mesh, but only because we have the subdivide. Without the subdivide, we'll lose a lot of detail. When we add the subdivide, you'll obtain back. You'll just get the detail back. So, and we'll insert a little attribute triangle, which is the main trick here. This is a nice workflow for blending two versions of the simulation. Because we did this whole thing with the rest attribute, so the simulation, baked simulation, contains the rest, which is the position, the animated position of the vellum simulation vertices or points. So basically this FEM has a version of the simulation which is not wrinkled in the rest attribute that we saved inside the final FEM simulation. Because of it, and because of the fact that we have the mask attribute that we painted on the static quad mesh and transferred it through this workflow to the FEM simulation, because of these two things, we can write this expression: VP equals lerp VP V rest 1 minus mask. So what it does, it uses the mask to blend our wrinkly FEM simulation and the clean, non-wrinkly vellum simulation using the mask. So if you visualize the mask, where the red is, we have the FEM simulation, where the blue is, it's the vellum. So using this version of the simulation, using this version, we're going to point deform our quad mesh and get this. So yeah, that's it. Let's disable this mask thing, and you can see that we have a wrinkly sim here. Yeah, so one thing we'll add here is, yeah, we have to display the, yeah, we don't have any color here. So in order to get the color, we can do maybe another thing, because we got the color and the velocity from the vellum sim, which is not a bad idea. So let's copy these guys here, and let's connect this and our vellum sim. That's animated. Yeah. So we're basically copying the color and the velocity from the original vellum sim, which is not bad. And the vectors are pointing downwards because the mesh is falling onto the ground, which is correct. And we're attribute casting, basically attribute casting these guys, the V, the N, and the CD. So we're saving a little bit of space here. Yeah, and we'll basically get rid of the group delete. We'll remove all the groups with the asterisk. And we'll also maybe remove the mask because we don't need it anymore. Let's do it with the clean. So clean, I like this node because it's universal, but it considers all the primitives as degenerate. So let's uncheck this. yeah, let's remove everything except a few like CD, N, V, yeah, and the UVs also. We want to save those, but something happened on the way. Yeah, no, everything's fine. We're actually casting this thing, but yeah, I'm gonna copy this output. And just name it differently. It's going to be called like this: sim main clean quadri wrinkled high, and set the range to 1 to 300. We're simulating 300 frames in general, and yeah, the FEM sim setup is done. I will simulate this whole thing and come back to you in the second lesson and in the next lesson about the flip simulation, which is going to be built on top of this wrinkled simulation. So yeah, looks cool. It's quite long, but I hope you understood the whole setup and how the workflow works with these kind of sims. Thanks for listening and watching. See you in the next one.